Right. In the last class, we discussed, let's quickly go through that. So we discussed what is encryption and decryption. Okay. Uh, some terminology related to encryption and decryption, plain text, ciphertext, uh, encryption algorithm, decryption algorithm, key. Okay. So then what is cryptanalysis? By the way, I have added a new node for this one, not new node. I updated this node with some past paper questions. Okay, so if you have already downloaded this from the Google Classroom, just download it again. Uh, and also I have uploaded the other node for today's class, that is Symmetric Key Cryptography. So if you have already downloaded this, re-download from the Google Classroom because the new node only have the past papers. Okay, past paper questions. Right, so we discussed what is cryptanalysis. That is analyzing ciphertext to guess the possible keys and possible algorithms. So this is a new slide I added because there was a past paper question on this concept as well. Steganography. So steganography is something related to cryptography, but something else as well. So basically, steganography is hiding some secret information inside non-secret media. So it's not encryption. So you have non-secret media like image, audio, video, right? And inside that non-secret media, uh, you have a hidden message or hidden, uh, basically a hidden message. So that is called steganography. Okay, so it's not necessarily encrypted. Okay, it's not necessarily encrypted because there was a past paper question. I just said that also. So that is called steganography, not cryptography. Okay. Right. So these are the features of steganography. So the purpose is hide the existence of a message. So therefore we can carry it through images, audio, video, maybe inside text also it may be there. Maybe those characters are mixed with a valid text, human readable text. Okay. So the idea is to hide your message to the possible attackers. And of course, for additional security, if you want, you can encrypt that also. First use steganography and then use encryption. So then even though someone managed to decrypt it, still he or that attacker may not be able to find it because it's steganography. Now he need to undo that also. Right. So last time we discussed about the classification, substitution versus transposition, stream versus block, with key versus without key, and with key, symmetric versus asymmetric. Okay. Right. So we discussed what is substitution cipher, what is transposition, right? Transposition means mixing. So then the stream cipher versus block cipher. In stream cipher, we do substitution or transposition character by character. Whereas block cipher, we do it block by block. And today, when we start doing symmetric key cryptography, you will find that some algorithms are stream ciphers, some algorithms are block ciphers. Okay. And both approach has its pros and cons. Okay. So block ciphers, you need to wait for a block of data. But stream cipher, we can just smoothly do the processing as and when and there, then and there when we get the data. But block cipher is better security. So these are very important for exam. Stream ciphers are less secure. So therefore, in fact, reality we use more block ciphers. Okay. And keys can be reused in block cipher, but in stream ciphers, you must not You must never reuse keys because stream cipher is a weak security. So if you reuse your keys, it can be even weaker. But some positive point about stream cipher is it's faster because then and there when we get character and character by character, we do the encryption. And also therefore it needs less memory. Whereas this is relatively slow and require more memory because we process block by block. And error propagation is also low here because we process character by character. But here, when you have block, say if there's some error in one place, so that affect not only that character, uh, entire block. So stream cipher is good for real-time communication where you can't have any delay. But for other situations or general situations, always block ciphers are preferred. It's a very important slide for you to understand, right? Because if you don't understand these concepts, after some time you will completely lost, right? Because we are going to combine these concepts, right? Stream. So, for example, is it a symmetric or asymmetric? And is it a symmetric stream cipher? Is it a symmetric block cipher? Does it use substitution? Does it use uh, transposition? So at the end, you must have that sort of a sense. Okay. Right. Again, we can do it without key, with key. But in practice, almost all the time we use a key. And again, we can use same key for encryption, decryption, or two different keys. So then symmetric versus asymmetric. Okay. So both approaches are used because today we are going to discuss symmetric key cryptography. Next class, we are going to discuss asymmetric key cryptography. So that means we use both. Okay. Right. So then we discuss some historic ciphers. Right. Starting with Caesar cipher. Okay. And you will see some past paper questions also. It's substitution cipher, character level substitution cipher without a key. It's a very weak cipher because you use the same algorithm for each and every character. And it's a symmetric, sorry, it's not key-based cipher. It's a uh, without key we use the cipher. Okay, without the key we use the cipher. So then monoalphabetic substitution, little bit better than Caesar cipher, but still a lot of patterns are revealed because one character is always substituted with the same character. So in order to make it a little bit better, we can go for polyalphabetic uh, substitution ciphers. So rather than one substitution table, we can use multiple. At the same time, we discuss about the Kama Sutra cipher because that is one of the first cipher with that use a key. Okay. Right. So then we look at the transposition ciphers, which do use permutation and also the mechanical form of that Enigma rotor machine, which was used in World War II to encrypt war-related messages and decrypt. And also we look at what is one-time pad is. It's a hypothetical perfect security solution under three conditions. Truly random key size must be as big as your message, key is used only once. If you do it, you get perfect security, but it's not very practical because every time you use a new key, then the same key is used for decryption. So then how do you communicate that key? Okay. Then we look at the Vernam cipher, which use a key and bit level XO operation. Burnham cipher. It's a very simple binary level substitution, character level, stream level substitution cipher, but actually it's a stream level and bit level, not even at character level. Right, so that is where we stopped. That is where we stop. So let's pick up from that point. Characteristic of good ciphers. So under characteristic of good ciphers, we are going to look at three aspects. Kirchhoff principles of effective ciphers, Shannon's characteristics of good ciphers, and the avalanche effect, another property of a good cipher. Cipher means encryption decryption system or algorithm. Right. We'll start with Kirchhoff principle. Now, at the end of each session, you must go through the UCSC note, right? Every topic I have uploaded the UCSC note as well. And also I have even highlighted more important features. Then you, so then you can compare it, our note. If there's anything new, you can study that also. But almost all the time, I try to cover everything in the UCSC note in our note. Right? Sometimes if I feel like it's too much details, I skip it. Otherwise, I always add it. Right? Kirchhoff principle. So it's a very simple principle. Okay. So it says security of your encryption system must depends on secrecy of the key, not on the secrecy of the algorithm. Not on the secrecy of the algorithm. So that means you must rely on the secrecy, keeping the key secret rather than keeping the algorithm secret. Okay. Because keeping the key secret is more practical than keeping the algorithm secret. Actually, in modern encryption decryption systems, almost all the time it follow Kirchhoff principle, where algorithms are well known. Not only it's not a secret, those are well known also. But we just keep our key secret. So therefore, though someone know the algorithm without the key, it's near impossible to guess. Okay, because we can time to time keep change our key as well. Changing the key is simple thing rather than changing the algorithms. Right. So that is Kirchhoff principles. So the next we move on to Shannon's characteristics of good ciphers. Shannon characteristics. So Shannon came up with 5 characteristics of a good cipher. So you need to remember these as well because they ask these in the exams. So what are those 5 characteristics Shannon proposed? Okay. Number 1, amount of secrecy should determine the amount of labor for the encryption decryption. So here the labor is not human labor, processing by your algorithm. So this is common sense. For example, if you need very high security, it's sort of a super critical, use very complicated algorithm. But if you need moderate level of security, it's not very critical data, but still you need some sort of security. Use moderately complicated algorithm because higher the complication, higher the computation power, the more time it take, there will be delay, right? So therefore, it's common sense. So don't over-engineer your encryption systems. Okay. Right. Second point says set of keys and encryption algorithm should be free from complexity. So yes, use complex algorithms, but technically implementation wise, it must be not that complicated. So in simple, this means use smart algorithms. Right. yes, you want to make it extremely effective encryption. That means there's no pattern. It's completely mixed ciphertext. But in order to do that, you don't need to make your algorithm extremely complex. Sometimes there are some simple algorithms which make your plain text into a very effective ciphertext. Right? So therefore, yes, make it very complicated so that hackers can't guess it. But at the same time, to make this into a very complicated ciphertext, your algorithm doesn't need to be as complicated as well. Sometimes your algorithm is very simple, but it does very complicated tasks. That is second. Third one says the implementation should be as simple as possible. Because once you have the algorithm, you need to implement it using Java, C, Python. So when you implement it, try to implement it as simple as possible because sometimes programmers can over-engineer. When you have an algorithm, when they put it into code, sometimes they make it overcomplicated. Okay, so make your algorithm simple and also make your coding simple, implementation of the algorithm simple. But make sure it does very complicated substitution, permutation so that the ciphertext is really, really tough to crack. But don't make your algorithm complex, don't make your implementation complex. Fourth one says errors in ciphering should not propagate. Remember, when you encrypt maybe a document into ciphertext. So if there, when you do the encryption, there can be errors, of course. Ideally, there must not be any errors, but say in case there's error. So if there's error happening encrypting this part, only this part must be unusable when you decrypt. It must not affect other parts. Maybe you make your system made a mistake encrypting this part, so then only this part must not be available or corrupted, not the entire plain text. That is what it says. Errors in the ciphering should not propagate and cause corruption of further information in the message. Okay. So the final point says Shannon's characteristic says size of enciphered text or size of ciphertext should not be larger than the text of the original message. So that means good ciphers will make your ciphertext not no bigger than your plain text. So when you encrypt, don't think that you want to make it bigger, right? No, without making it bigger, still you can mix it, substitute, transposition, and if it is 1 kilobyte, you can make sure that this is also 1 kilobyte. That is possible because we don't make it complicated by making this bigger. Because if you make it bigger, then you need more storage, more bandwidth to store your ciphertext, transfer your ciphertext. That is not the purpose, right? So those are the 5 characteristics. We call them Shannon's characteristics of good cipher. So earlier we discussed Kirchhoff principle. You must depend on secrecy of algorithms, sorry, secrecy of key, not secrecy of algorithm. But this is 5 characteristics. Okay. Right. The final one is avalanche effect. It's another characteristic of a good cipher proposed by another person. Now it says small change in plain text must produce significant change in ciphertext. Okay. Say this is the message you send today. Say hello. So then this is your plain text, ciphertext. QTU $3 M Okay. Now let's assume now this is done by your encryption system using a key or something. Now let's see next day your message is hell. Just O is missing. So if you follow avalanche effect or if your algorithm follow avalanche effect, though this is just one character change or missing, so this must be completely different text now. Say 3W hash 3Q or something. So though this is just one place, one character missing, so ciphertext has come changed to change almost something new. That is called avalanche effect. So good ciphers will make it. So even when there's a small change in your original plain text to a new plain text, there's a big change in the ciphertext. That should be the case. That make cryptanalysis harder for the hackers. If anything is not clear, ask, okay? These are the very basic things that I'm doing it faster. Right. So we discuss Kirchhoff principle, Shannon's characteristics, and avalanche effect. So let's discuss few more theoretical aspects and finish it. Okay. Right. Levels of security. So when it comes to information system security, we can look at two levels of security. Right. Unconditionally secure, computationally secure. Okay. Unconditionally secure means this is for encryption decryption. Okay. So say you got some ciphertext, set of ciphertext or whatever. Now you want to analyze these and try to see what is the key, what is the algorithm. Maybe you know the algorithm, you want to guess the key. But if your encryption decryption system is unconditionally secure, it doesn't matter how much of ciphertext someone analyze, they should not be able to uh, come to a conclusion at all. It's unconditionally secure. No way they can analyze this and find the pattern, right? So that then we say our encryption decryption system is unconditionally secure, which is good, but usually this make a lot of complications, require a lot of processing and so on, then delays. In practical sense, you don't need unconditional security. What we need is computationally secure. So this means forever you can't find it, even though you keep processing forever. Computationally secure means the cost of breaking the ciphertext exceeds the value of the encrypted information. So when we say cost, it includes both money and time, right? Cost. Remember, there's a statement says time is money. So therefore, your cost means both time and money, or money and time. Computational secure means yes, maybe one day you may be able to analyze these ciphertext and find out what is the keys and thereby what is the plain text is. But by the time you do it, because you are going to do it by a lot of processing, by the time your computer does it, this plain text or this ciphertext useful lifespan must be ended. So then it is good enough. We don't need unconditional security. But if we can make sure that, say, so the useful time period for this data is 1 year. But even a very high speed supercomputer can't analyze and break it within 1 year. That is good enough. Because after 1 year, the usefulness period is over. Okay. So the time required to break the ciphertext exceeds the lifetime of the information. So that is good enough. That is good enough. We don't need unconditional security. We don't want to, we don't need to make sure that forever this can't be cracked. No. Okay. Right. So let's look at the type of attacks, little bit more theory. Okay. So there are so many type of attacks, but we are more interested in attacking crypto system, encryption, decryption system, or attacking ciphertext to guess the plain text or key. Okay. So first one is brute force attack. So the word brute force, brute means blunt, right? Blunt. Blunt means not smart. You rely on sheer processing, okay, rather than try to be smart. So brute force attack means basically for an encryption decryption system, you try all possible combination of values and try to guess what is the actual value is. It's like you have a lock and you have millions of keys. So you start using one key at a time. They say those are different keys and try to find out because you feel like one of the key is going to open this, but you have no other clue. Therefore, you just take one by one, but you have millions of keys. So this is like that. You just try A, then A B, then A B, A C, then A Z, then B A, so then Z Z, then maybe A. So you try out all these until you get the correct key, correct, okay, plain text. Then of course you must have a way to verify whether it's correct also. Otherwise you may get the correct one, but still you don't know whether it's correct. But if you don't use any other smart technique, and if you just rely on trying one by one, so that is called brute force attack. Right? Brute force attack. Okay. So that is why we try to use long keys and try to use all combinations, not only characters, special characters, numbers, and also try to make it longer, like 10 characters, 8 characters. It's better than just 3 characters because then maybe just the millions of possibilities are there, not even millions, sometimes thousands. Okay. For example, say you have 3-character password, 3 character. Let's assume you can have used on the alphabetical, you have used on the alphabetical, and there's a restriction saying on the alphabetical. So then this can be one of 126. This is one of the 26. Let's assume simple capital also not there. Otherwise, it is 52. If you consider simple day is different from capital day. So then how many possibilities? 1 over 26 into 1 over 26 into 1 over, or number of possibilities is 26 into 26 into 20. This is not huge, right? Maybe few thousands. So when you start A to Z, out inside this your password is there. Even though you execute a brute force attack. So that is brute force attack. But if you have more characters, maybe 8, 10 characters, and you allow special characters, numbers, now it is no longer 26. Maybe you have, I think maybe keyboard you have about 60, 70. Then if you have 5 characters, 60 into 60 into 60 into 60 into 60 possibilities. That is huge, right? Possibilities is in millions. Or when we increase it, it will go into billions. Like even so the idea is make it stronger so that brute force attacks will be ineffective. But if your keys are weak, like just only selected letters, uh, short keys are asking for troubles. But this is the very primitive approach. Another possibility is dictionary attack. In dictionary attack, we have a dictionary of popular passwords or popular keys. Right? So some people they have not some people in general people have some common. Sometimes they just use the default password of the system like root, or sometimes they just use something like 1 2 3 4. Or there are some common things like say Sri Lanka. If someone is from Sri Lanka, they might use something like Sri Lanka, or sometimes they might use the month of a day, year. So those are possible keys. So dictionary attack means those dictionaries have those popular passwords, and then they try one by one from the dictionary. It's not like brute force attack. It's a little bit smart, but it doesn't guarantee that you find the password, because that is why you must set a very unique password. Don't go for these common password, because if dictionary attack is there, probably you will be caught. Your password will be guessed. So that is why you need to come up with a strong password, not common passwords. Okay. Right. So next one is rainbow attack. So remember we discussed that in hashing, we save the password with a hash value, right? And also to make it a little bit more stronger, we can add another string and then take the hash and so on. Okay. So most of the time we save our password as a hash, as a hash. So rainbow attack means we try to guess that hash value also. Okay, so there are pre-computed tables of hash values. And we use those hash tables to guess your password. So then we say rainbow attack. Okay. So brute force attack, dictionary attack, rainbow attack. Right. We can't forget about the human factor. Of course, we did not cover all the possible attacks. Okay. So you can talk with ChatGPT and add more items to your list. Right. So we can't forget about the human factor when it comes to securing your encryption decryption system, security system. Right. So maybe some internal people in your organization with vicious intentions. Sometimes it can be a mistake, intentionally try to crack your system. Okay. So that is why we need highly professional people involved in your organizations, developments, operations, and so on, so that they don't, first of all, they are very competent and they are aware of these possibilities. Secondly, they are very moral and ethical people, so they don't compromise security for gains, personal gains. Okay, right. So let's move on to the past papers. Okay, so we cover the last 3 years of past papers in the class itself. Okay. Right. So there are some questions you just need to say true or false, but you need to explain. Right. You can't just say true or false. Just you need to write true or false, and then you need to explain why is it true, why is it false. Okay. Right. So this question I already that actually because of this question I added that part to your note. Steganography. So is it true or false? Steganography is the study of the breaking codes and ciphers. True or false, anyone? Is this steganography? So how do you call this? How do you call this? Study of breaking codes and ciphers? Study, because we discussed that last time. Today also I mentioned. So that is called cryptanalysis. Right? So that is called cryptanalysis. So therefore, steganography is hiding your message inside another message or picture, audio. That is steganography. Right? So therefore, this is false because this explains not steganography. Maybe you can say that because you need to explain the answer, you can say that steganography is hiding the message within another message, whereas study of breaking codes and ciphers is called cryptanalysis. So likewise, if you write a good explanation, definitely you will get the full marks. So don't just write true and false and come home. Okay. Right. Right. Next one. That is 2023 1B. Right. 2022 1A. A transposition cipher replaces one character with another character. True or false, you need to explain. Right? Transposition character cipher replace one character with another character. So if one character is replaced with another character, that is called substitution cipher. Right? Substitution cipher. Transposition cipher is you change the position of the characters or blocks. So you better explain both. Why this is false and what is the correct answer for this. Right? Right. Substitution cipher replace one character with another character. One character or block of characters. But because the question use character, answer also has use character. Okay. So then if I go to the exams, I will explain what is transposition cipher also. Then I will say whereas the transposition cipher change the position of the characters or blocks. Transposition. Okay. That is called diffusion. So the purpose of substitution is confusion. You may make a small note of that, right? The purpose of substitution is called confusion. The purpose of transposition is diffusion. Sorry. Diffusion. Right. So not much questions because this is just introductory topic. Okay. Right. So now we move on to our next subtopic. Next topic, symmetric key encryption. Okay. Right. Symmetric key encryption, decryption, or symmetric key cryptography. So you know what is symmetric key cryptography is. If you use the same key for encryption and decryption, we call it symmetric. Symmetric, okay? Same key. Now, so there are pros and cons. Remember, we have two options, symmetric key, asymmetric key. Okay? So we have the plain text, we encrypt using encryption algorithm, but with a key. And then the ciphertext is sent to the receiver. Receiver decrypt this with the same key as we use for encryption. So that is called symmetric key. Another name is secret key. Another name is private key. Right? Symmetric key, private key. Okay. Symmetric key, private key. Right. So the main advantage, anyway, we will look at the advantages and disadvantage at the end also. So this is very simple and efficient because the same key is used. And you need less computational power. And therefore it's efficient as well. But this approach has serious drawback, that is the key distribution issue and scalability. Okay, so we will look at those disadvantages at the end. Right. So that is why to overcome these disadvantages, we have another approach called asymmetric key cryptography, which is our next topic anyway. Okay. Right. So symmetric key cryptography, that means if you use the same key, remember we can use uh, stream algorithms or block algorithms. Stream means we encrypt character by character. Block means we encrypt block by block. Okay. So both approaches are there. We will look at both these algorithms for symmetric key. Right. First, we will look at the block ciphers because block ciphers are the more commonly used ciphers. Stream ciphers are a little bit weak in security, whereas block ciphers are more stronger. Okay, strong algorithms. So we will look at some of these block cipher algorithms. So you need to remember these names, and especially these two, you must be really serious about how these three algorithms work because in the when we do past papers, you will see a lot of past paper questions. Okay, but we are more interested in DES, AES. So then IDEA, Blowfish, RC5, RC6, Cast 128. So those are also some of the symmetric key block ciphers. And finally, we will look at one of the stream cipher, that is character by character encryption, decryption is done. That is RC4 cipher. RC5 and 6 are block ciphers. You can see the newer versions of the RC4 is also block ciphers. Now you can see the trend, right? So the trend is going more and more towards block ciphers. Right. So the main requirement for successful symmetric key cryptography is your key must be secret. It must be a secret only between sender and receiver. No one else must know it. And also because secret key, symmetric key algorithms are a little bit weak compared to public key algorithms, you need strong algorithms. Okay, strong algorithm. At the same time, you must make sure that your key is not compromised. Okay, key is not compromised. But in public key, asymmetric key cryptography, actually, one of the key is public, but you don't have that kind of a luxury here in symmetric key cryptography. You must make it secret, secret between the sender and receiver. Right. First, we look at some of the cipher symmetric key block ciphers. Then finally, we will look at symmetric key uh, stream or character ciphers. Okay. So you will learn a bit of theory. Sometimes you may find it a little bit boring, at the same time, it's a little bit intimidating, thinking that, okay, it's huge headache. But that is why you need to do past papers. So in the class, we do 3 years of past papers. I recommend you to do another 3 years of past papers. That means altogether 6. Then you can get idea about what kind of things examiner asks. Though you learn a lot of theory, examiner has favorite areas. Okay, examiner has favorite areas. Most of the time, same sort of a question is repeated, right, in this kind of a topic. So therefore, if you first study and then go for questions, exam questions, you will find that you have wasted a lot of your time and energy, right? And a lot of frustration at the same. So the smart way to do this kind of subject, study in this kind of subject is go through the note, don't, of course, try to understand everything, but don't memorize everything. So then go to the past papers and decide which are the examiner's favorite areas and try to focus more on that. Otherwise, it's near impossible to memorize all these things. Right. So therefore, that is why today itself we are going to do the past papers. Okay. Right. So the first concept, now remember we are into the symmetric key block ciphers. symmetric key block ciphers, and there are a large number of symmetric key block ciphers in your syllabus. DES, AES, IDEA, Blowfish, RC5, RC6, CASP 128. So, okay. Right. Some of the symmetric key block ciphers use what is known as Fiesta network. It's a design model. Right? It's a design model for symmetric block ciphers. So therefore, some of the block ciphers use this approach or this model. Okay. So the basic idea of Fiesta network is, so far they have not asked anything on this, but there's a high possibility that maybe in your exam they will ask something about Fiesta network. I'm pretty sure. Okay. So this is the process. If a cipher, if a particular block cipher use Fiesta network as the design concept, so your plain text, remember block cipher means you process it as blocks, not as characters. Characters means stream ciphers. You say you have some text, hello, Nimal. So you break it into small blocks and then do the encryption. Okay. So for you don't like these blocks, sometimes block of 4 byte, block of 8 byte, because we encrypt huge documents and so on as well. We will look at those block sizes also. One of the examiner's favorite question. What are the block size? What is the block size? What are the block sizes of certain ciphers? Right. So if you use Fiesta network, this is the framework. This is the basic structure. So you break your block into two parts, left half, right half. So each block is further subdivided into two and then proceed or then encrypt it. Okay. And each step, only one half of the block is transformed, the other half is swapped. So it's a step-by-step process. You do it in steps. That means you keep encrypt it, encrypt it, encrypt it until it's strong. It's a stepwise process. Step 1, step 2, step 3, step 4. Okay. Each step, only one half is processed. Other half is just copied. That is the second feature of Fiesta network. Okay. Other half is just swapped. And the other thing is, in the next step, your right half is your left half is right. But your left half is process and make it right. But right half is just copy. Okay, so that is your second property. And the third property is each round, that means we do it in rounds. Right? We do both substitution and permutation. I told you that most of the algorithms use both substitution and permutation because that is better rather than just doing substitution. Now remember, one of the drawback of uh, Caesar cipher is it's only the substitution. There's no permutation and also no key, and also it's a character by character substitution, right? And a lot of weaknesses, right? But if you use Fiesta network, it uses both substitution and permutation. So you break it into two halves. Only one half is encrypted, other half is copied in a one step. Of course, in the next round, yeah, non-processed half is now getting encrypted. So therefore, at the end, everything is encrypted. But at a particular round, only one half is encrypted, other half is just copied. And we use both substitution and permutation. Okay. So this is not related to a particular algorithm. This is related to set of algorithms as long as those algorithms use this design idea. So this is the diagram. So this diagram is from your note. So you can see this is encryption process and this is decryption process. So therefore, this ciphertext is the input to the decryption process. And at the end of the decryption process, you must get this original plain text. හොඳට මේක දිහා බලන්න ඕනේ. ඒක deep මේක දිහා හොඳට ගැඹුරට බලන්න ඕනේ. You spend some time, quality time. නිකම් මේක උඩින් බලුවට තේරෙන්නේ නැහැ. Okay. So this is the encryption process, decryption process, and you can see that it happens in steps. So this is step 1, step 2, and this is step n. Now තේරෙනවා කලින් කියව කතන්දර ටික තියෙනවා කියලා. Right? Right. So this is your left half, right half. This is one block, and this happens to each and every block. Okay. And you can see that this right half is encrypted using a key. Okay. And then it is combined with the left half. Okay. Combined with the left half. Now you can see that it is getting swapped also. Your left half, right half is now your left half. But you can clearly see that this part is encrypted. This part just go as it is, going as it is. Sorry, I made a mistake. Your left half is encrypted, but this encrypted part is used to further encrypt the left half, but the right half is just going as it is. Right? Your right half is not encrypted, only the left half is encrypted. But to encrypt the left half, we use the right half. But to encrypt the left half, you use the right half. But in reality, your right half is just copied as the left half. Okay. But in the next step, that part is encrypted. You can see this is where the encryption happens. So this is XO. In step 1, right half is not encrypted, but now right half is encrypted. This time, the result of the left half is not encrypted because it's just getting copied to the next level. It is encrypted to make right half encrypted. But that is not the encryption of the left half. Your left half is just copied. So likewise, it's going through your steps. Right? Going through your steps. So therefore, each step, your left half is encrypted. But at the end of encryption of the left half, for the next round, it is your right half. Last round's right half is your left half. Last round, the right half is not encrypted. But now it is encrypted. දැන් හිතන්න පුළුවන් මෙන්න මෙතනින් මේ right half එක encrypt කරනවානේ කියලා නෑ. Right half එක මෙහෙම copy කරනවා. මේ encrypt කරේ මෙයාව encrypt කරන්න තව ටිකක් strong කරගන්න නේද? අපි කිව්වොත් මෙයාව encrypt කරන්න අවශ්‍ය තව මේ දෙයක් තමයි මේ ගත්තේ. ඒකට තමයි මේවා පාවිච්චි කරන්නේ. මෙයාව නැත්තම් නිකම්ම copy වෙනවා. හරි? So right half is not encrypted. But now that part is encrypted. For that, you use the previous left half to create that additional text. Okay. Likewise, each step, half of the block is encrypted process. And we can encrypt it many times, maybe 10 times, so that it's very strong now. And here, of course, you are doing the reverse of the stuff so that you ended up with the plain text. Okay. Right. So that is called Fiesta network. How many rounds do we do it? So it depends. It depends because this is a network. This is a design idea. How many rounds you do it depends on your algorithm because this is not an encryption algorithm. This is design framework. How many rounds is determined by your algorithm. Okay. And this happens at bit level. Okay, bit level. So this is how you write it. Okay, this is how you write it. left I plus 1 is right I. So you can see right 0 is your left I plus 1. Right 0 is your left 1. It simply copied. Left I plus 1 is right I. Left 1 is R right 0. Left 2 is right 1 because this is simply copied. Right? But what about the right I plus 1? That is this one. Right I plus 1 is left I XO with after encrypting the right I with the key. For the first one, it is R0 and K0. For the next one, it is R1 and K1. And finally, it is Rn and Kn. And so this is used to process this, right? So this is encrypted to process this, but your Ri is just your next line. Okay, next line. And of course, in the decryption, it is a reverse. It is a reverse. So you can simply see that Ri is Li plus 1. Okay. But Li plus 1, Li is now Ri plus 1 XO this. Right? It's a simply the reverse process. I don't think that they will ask these formulas, but they will ask, check whether you know the idea behind this Fiesta network. Right? Swapping of left, right. The right hand side is not encrypted in each step, but next step that will be encrypted because your right hand side become left hand part. But each step, the left hand part is encrypted. So ultimately, if there's a 10 step, your left hand side is encrypted 5 times, right hand side is encrypted 5 times. And ultimately, it's fairly strongly encrypted. And in these algorithms, they use both substitution and transposition to make it strong. Okay. Right. So that is Fiesta network. Fiesta network or the Fiesta design. Now we look at what are the three popular symmetric key algorithms. But other than these, we are going to look at few more. But these are the three that we are going to look at in detail. Right. So there are few more. So those things we will just mention. Okay. So look at this diagram. First one. Right. So we are going to look at in detail these three. DES, AES, and there's something called triple DES also. It's variation of DES. But we are going to just briefly look at these things, but we are going to look at these things in more details. Okay. Right. So let's start with DES. So these are very popular algorithms. Almost every year they ask about DES, right? AES and so on. Right. So DES stand for Data Encryption Standard. DES. So this is symmetric key block algorithm. So DES is a symmetric key block cipher. This is the most widely used block cipher, especially historically. And it uses Fiesta process. That is why we discuss about the Fiesta network first. Right. So this used to be very popular, but now people have found some controversy or the loopholes in this algorithm. So that is normal. When the computing power is getting better and better, right? Algorithm that used to be safe become non unsafe. Sometimes the vulnerabilities are found later. Sometimes the vulnerabilities were there, but at that time computational power was not good enough to make it break it fast. But now we can break it fast. So therefore, in modern context, we don't you don't use we don't use DES. We don't use DES, but DES used to be the most popular for very long period. That is why it is in your syllabus. And also there's a variation of DES which is fairly good. Right? Because DES, when DES got some issues, controversies, so they came up with another variation of DES called triple DES, which is strong. Okay. Right. So DES is obviously block cipher. And block size is 64 bit. This is something you need to remember. ඔන්න මේවා තමයි එක්සෑම් එකේ අහන්න දැන් පාස් පේපර්ස් වලට ගියාම තියෙනවා. ඒක වදයක් තමයි කරන්න දෙයක් නැහැ. ඉතින් එක්සැමිනර්ට අහන්න වෙන දේවලුත් නැහැ මේවා security subject එක. Right. So DES is data encryption standard, block symmetric block cipher. Block size is 64 bit. So it break your message into 64 bit block and process. And remember we use key because this is symmetric key. And the key size is 56 bit. So these are the super important thing for exams. So they almost every year ask what is the block size of DES or what is the key size of DES. Okay. So in reality, the key size is 64 bit, but 8 of those are parity. So therefore, effectively 56 bit. So therefore, in the exams, if you see the key size as 56 bit, take it as an answer. If you don't see 56, rather if you see at 64, still you can take it as answer because then maybe examiner has taken the full width as the key size, right? Because with parity bit, it is 64 bit. If you exclude the parity bit, it is 56 bit. So therefore, just consider both as correct answers. Okay. But most of the time, they say that it is 56 bit. And you ask about, one of you asked about how many rounds you process it. If it is DES, it is typically 16 rounds. Right? So 16 rounds means you need 16 intermediate keys because each round we change the key. Right? Remember, each round we change the key. You can see K1, K0, K1, K2, K. So 16 round means we have 60 internal keys. Right? So that means from this key, 56 bit or the 64 bit key, the algorithm internally generate, if it is 16 rounds, 16 different keys based on your key. Okay. 16 intermediate keys. Right. 16 intermediate keys. But these intermediate keys are 48 bits. Your key is 56 bit. But intermediate keys are 48 bit because from this 56 bit key, it generate multiple number of intermediate keys. Because each step you need key. K1, K2, K3, K. Okay. As I told you, key is 64 bit, but only 56 bits are effective because other 8 bits are parity. Okay. Which is huge actually. There are this much of possible keys, so therefore someone guessing the key is very rare. Very, very rare because it's 2 to the power 56 number of possibilities are there. Right. As I told you, now there are vulnerabilities for DES algorithm. Though it happened to be the most popular, right now we don't use it because cracking is possible. Okay, cracking is possible. You can see how it evolved. 1997, the cracking take few months in 1997, but in 2010, right, few minutes. Within few minutes, with strong computing machines, it can be cracked. So that is why we have some alternatives for DES. Because right now DES is not safe. Right. So one of the alternative is triple DES. So triple DES means we still use the DES algorithm, but we use it 3 times. That is why we call it triple DES. Internally, a DES algorithm also has steps, maybe 10 steps, but now that kind of a thing also we do 3 times. Right? That kind of a full step is now repeated 3 times. So then we call it triple DES. So triple DES is stronger than DES. Okay. And it is good enough for real time, real world encryption. Remember, DES has vulnerabilities, but not triple DES. But at the same time, triple DES is slower. That is obvious because triple DES do it 3 times. Right? So those are the things you need to remember, understand, examiner's questions, right? So now you should compare. DES has vulnerabilities, but not triple DES, right? Triple DES is slower than DES, but stronger, better security. And we can do triple DES in 2 different ways. What are those 2 different ways? We can do triple DES with 3 keys. That means each round we use one key. First round, first key, second round, second key, third round, third key. Or else you can do the triple DES with only 2 keys. So that means one particular key is used twice. Okay. So this is if you use 3 different keys. So this is your plain text. You apply DES using your key 1. Then to that ciphertext, you again apply DES with your second key. And to that ciphertext, you apply again DES using your third key. So that is triple DES using 3 different keys. And this is your final ciphertext. So this is how you write it. Plain text is encrypted with K1. And that one is decrypted with K2. And that one is encrypted with K3. Now, when you see this, sometimes you might get confused. Do you have any confusion about this? Any question about this? So you encrypt your plain text with K1, then decrypt using K2, and then again encrypt using K3. Maybe all of a sudden you will not get this question, but if you study this, so when you study, you think hard, right? Think little bit you go into long depth. Sometimes when you go into that kind of a serious thinking, you might feel like, okay, this is crazy, right? You encrypt and decrypt. So when you encrypt and then decrypt, what you get is original text, right? So you encrypt something and again you decrypt. So then you must get the original. So then what is the use of this? Then you only encrypt it once. Because you encrypt and decrypt, then you are again with the original text, then you encrypt it. So this looks like you are just doing encryption only once because this is just doing an undoing. But it is not doing an undoing, though it looks like that. Why do we say that it is not actually doing an undoing? Remember, this is symmetric key cryptography. DES is a symmetric key cryptographic algorithm. So if you use the same key only, it is doing an undoing, or you get the same result. But this is different key. When you use different key, your decryption is also like encryption. Because when you use a different key, your decryption is not going to take you to the original thing, it's going to make it further encrypted. Okay. So that is why we use encryption, decryption, and encryption, but three different keys. Okay, so just pay attention because otherwise you may think that okay, three times doing encryption. Yes, it is three times doing encryption, but we do it in a sort of a encryption, decryption, encryption because this decryption is also encryption because we use different key. If you use the same key, yes, this decryption will take you to the original text, plain text, but not when you use a different key. Okay. And of course, this is the reverse process. So there we use first K3 because you want to do the reverse process. First K3 to do the uh, decryption, right? So then you do use K2 to do the encryption, and then you use K1 to do the decryption. You can see it's completely reverse. Earlier K1, K2, K3, now K3, K2, K1. Earlier encryption means now decryption. Earlier decryption means now encryption. So this is serious stuff. So this is called triple DES, right? Triple DES. No, these are three rounds, three steps. Triple DES. Step one, step two, step three. And each step you may have multiple rounds, maybe 10 rounds. Right? These are the three three times you do it. Each one is something like this. Right? Each one is something like this. Therefore, each round will have for each step. For step one, step two, step three, each step will have maybe 10 rounds. Right. So that is triple DES using three different keys. Similarly, we can do DES, triple DES using two different keys also. Rather than K1, K2, K3, we just need K1 and K2. Right? So this is how you do it. Now we have K1, K2, K3 is same as K1. Okay, so K1, K2, but K3 is same as K1. K1, K2, K3 is same as K1. Right, you can say K1, K2, K1. Why? K3 is same as K1. Other than that, it's the same formula. You encrypt using K3, sorry, you encrypt using K1, then you decrypt using K2, then you again encrypt using K3, which is K1. So now the reverse process you can always derive by yourself, right? Remember, this is encryption, decryption, encryption. So therefore, this is decryption using K3, sorry, decryption using K, is it K1 or K3? I think this should be K3. Okay. K3, this must be K2, this must be K. Yeah. So this is, of course, when we use two keys, right? Yes. So when we use two keys, remember your K3 is K1. So therefore, this is K3, but K3 is equal to K1, then K2, then K1. Yes, this is correct. This is correct. Because this is basically using two keys. So this is actually K3, right? But remember K3 is K1. That is therefore K1, K2, K1, and encryption become decryption become encryption, right? Reverse process. That is how you do the triple DES. And of course, triple DES is strong, strong, but it's slow. Okay, right. So there's another alternative now. that is AES. AES. So AES is stronger than even triple DES. So that means even triple DES is also effective, but triple DES is slow because you need to do that 3 times. AES, DES 3 times. AES is a different algorithm, which is better than triple DES. But it's again block cipher. Why do we call it better than DES? Because it's faster and stronger. That algorithm is giving you much stronger ciphertext, much lesser time taken. So therefore, in modern cryptography, symmetric key cryptography, they prefer AES over triple DES also. And DES is outdated. Triple DES is good enough, but AES is even better. And again, you need to remember the block size because it's a block cipher, 128 bit. And the key lengths, you have 3 different sizes depending on your requirement. මේක අනිවාර්යෙන් මතක තියාගන්න. What are the 3 possibilities? 128, 192, 256. Block size is 128 bit or 16 bytes. And again, it does 10 rounds of processing, but it's single step. Though we have 10 rounds, it's not triple DES. You do it only once. Okay. And decryption algorithm is not identical to the encryption algorithm. And this is much stronger and faster than even triple DES. Okay. Like AES. So this is again something mentioned in your note. Therefore, I just put it into our note also. But I don't think they will ask anything on this slide. But maybe you can remember a few words regarding AES. Just to get some clues about what is the high level idea about AES algorithm. Right. So the input to each round is 4 by 4 array of 120 byte plain text. You remember we process plain text, block of plain text. So when we use AES, we take the first block of plain text into a 2D array, 2D array, and then we process it. Right. And during that processing, each row is shifted. You can see this is shifted once, this is shifted two, this is shifted three, and this is not shifted. So shifting is not the only processing, but at the end, this shifting also happen. Okay. And the shifting is also zero row shift 0 times, first row shift one, second row shift two, and so on. And finally, you again get 2 by, sorry, 4 by 4 array after all your rounds are completed. Okay, all your rounds are completed. So therefore, if they talk about 2D array shifting of rows, definitely they talk about AES algorithm. And AES symmetric key block cipher algorithm. Okay. And again, remember AES use 10 rounds of processing. Okay. And your final ciphertext is the 10th output. 10th output. Okay. Right. So now we move on to PKCS5 padding scheme. This is not a algorithm, right? So now we have discussed 3 algorithms: DES, triple DES, AES. So this is a padding schema, right? Padding schema. So why do we need padding schema? Remember, we process data as blocks. Blocks. So this block, this block, this block, this block. And we have fixed size blocks. Okay, fixed size block. Each algorithm says what is the block size. But your data may not equally fit into this. Say, for example, my each block is 4 byte. If I have 16 byte of data, yes, perfect. But what happened if I have 18 byte of data? Then my last block has only 2 byte. But our block size must be 4 byte then. So then you need to pad it. Pad it. Because our algorithm always expect, say, 4 byte, assume. So only the last block you need to pad. Right? So let's assume it is 8 byte. Then if you have, say, 3 byte, you need to pad 5 byte to make it 8. If you have 4 byte, you need to pad 4 byte. Okay. And if it is 7 byte, you need to pad only 1 byte. What happens if you have all 8 byte? So don't think that you don't need to pad now. Now you need to pad 8 byte block. Full block is added. This is a very famous question. So don't think that when your block is filled, you don't need to pad. That is where you need the longest padding string. So therefore, always padding is there. Always. Okay. Right. So remember now we have discussed 3 block cipher algorithms: DES, triple DES, AES, and also a padding schema called PKCS5, where always padding is done. Right, now we move on to another subtopic. Still we are in block cipher, symmetric key block cipher algorithms. Right. So we have block cipher modes. මේටි පටලවා ගන්න බෑ. හරි අපි ඉස්සෙල්ලම කතා කරා Fiesta framework, which is designed for the block ciphers. Then we discuss the padding schema for block ciphers. At the same time, now we have discussed 3 algorithms: DES, triple DES, AES. දැන් අපි algorithms වලට තාම යන්නේ නැහැ ඉතුරු. මේ අපි යට තව algorithm තියෙනවා. But before moving to that, those other block cipher symmetric algorithms, let's look at another concept related to block ciphers called block cipher modes. Block cipher modes. And this is another important topic the examiners ask, and this is one of the tricky area examiners can ask tricky questions. And of course, already we'll see that there are tricky questions from this topic. Okay. Right, what is the time now? Right now it's 8:50. So today we want to give priority to the security, because if I stop it middle, next time again I need time, right? So therefore we will give priority to finish this topic today. Okay. Right, and do the past papers and finish it today. Right. Block cipher modes. So these are related to, again, symmetric block ciphers. So we are going to look at 5 block cipher modes. What are those? Electronic code book, cipher block chaining, cipher feedback, output feedback, and counter. So those are the 5 block cipher modes. Okay, in your syllabus. Let's take one by one. First one is electronic code book mode. This is the simplest mode. So basically what is mean by block cipher mode? So when we do block encryption, right? Block encryption. So we need to we need a tactic, or we need a strategy. How are we going to do that? Sometimes we want to do block by block, sometimes we want to mix those blocks, and so on. That is why we call it block modes or cipher block modes. So out of these block modes, the simplest is electronic code book mode. Okay, electronic code book mode. So this is your plain text. This is your first block, second block, third block, and it goes like that. And each block is separately encrypted. So this is your key encryption algorithm, So that means your plain text is subdivided into block, and each block is separately encrypted. Simple as that. So if you do like that, we call it electronic code book mode. Okay. And decryption is each block of ciphertext is now decrypted to get the corresponding plain text. Same key because it's symmetric. So here we keep encrypting block by block. So these are the resulting blocks here. And now decryption, you just decrypt block by block. It's super simple approach. Okay. So that is called electronic code book mode. So this is the simplest approach. There are advantages and disadvantages. So the main advantage is this is obviously simple, right? And also errors are not propagated, because if there's error in this encryption of this block, it is not going to affect other blocks, right? It is not going to affect other blocks. Only this block is now corrupted. All the other blocks can be decrypted to the original, exact original. Right? Errors are not propagated and simple, right? And also we can do it parallelly. That is another advantage, because these are independent. So these are all important. But other block modes you can't do like this. Other block modes pretty much you need to, your second block depends on the first block. Right? So what are the advantage? Simple to implement. We can parallelly process blocks, and errors are not propagated. If there's error in a block, it only affects that ciphertext. Okay, so those are all advantages, but there's a big disadvantage because you don't mix those blocks, patterns are not very effectively hidden, right? So if, for example, if there's a same block here, say this is high, this is also high, you get the exact ciphertext. So this ciphertext is same as this ciphertext. So therefore, it tend to retain patterns. It's something like this. So this is encrypted, but still you can see it has a bit of original nature because it doesn't mix up things. That is big disadvantage. But obviously it is simple, fast. We can do parallel processing and so on. Okay. But this is a big disadvantage. So if you have just few blocks, this may be good enough. But if you have a lot of blocks and if you want to 100% hide patterns, don't go for ECB. Right. Second block mode is cipher block chaining, CBC. Actually, you don't need to exactly memorize how it is done in the exams, right? But you must have a little bit of idea, understand, but don't memorize. Then you must know what are the pros and cons of each mode. That's it. So the examiner asks pros and cons or any unique features, rather than examiner asks to draw a diagram and explain what is it. Okay. Maybe examiner can ask you to do it for the first one because it's so simple. I don't think that for any other modes, actually examiner has only asked you to draw and explain it only for ECB mode. But other modes, you must know the pros and cons. But this is for you to understand. not for you to memorize. Okay. Right. CBC, second mode, cipher block chaining. As the word says, it's bit of chaining. Actually, all the other remaining block modes are doing bit of chaining. So here we have taken DES as example. So it can be DES, triple DES, AES. Okay. So there what we do is we take block by block again because those are for the block ciphers. These are block modes. And first block is encrypted. Get the first ciphertext. Second block is encrypted to get the second ciphertext. Third block is encrypted to take the third block ciphertext and so on. But your first ciphertext depends only on the first block, and there's something called initial value. Right? Those two are XORed and give it as the input, and then the key is there. So therefore, your first ciphertext block depends on your first plain text, initial value, and key. I will explain what is initial value next. Okay. Then what about the second block? So second, the input to this encryption is your second block and your first block ciphertext. You can see first block ciphertext, and then you get the second block ciphertext. For the third block, the second input is second block ciphertext, XOR, and then apply the algorithm to get the third block, and so on. So that is why we say cipher block chaining. So this ciphertext is chained to the second encryption. Second ciphertext block is input to the third encryption, one of the input, and so on. So therefore, before your plain text is encrypted, it is XORed, right? XORed with the previous ciphertext and then only encrypted. And that one is your encryption. At the same time, it becomes one of the input for the next encryption. So that is called cipher block chaining. And now it's stronger because each small change here will change all these ciphertext, because small change in plain text here means this is different now. This is different means now this is different because this is input. This is different means now this is different. So when you do a small change here, all these ciphertext are changed. So remember that small change in plain text must result in big change in ciphertext. One of our good feature. So that good feature is there in CBC, which was not there in electronic code book. Now patterns are effectively hidden. For example, here also it is high, here also it is high. Maybe here it is something like this, but now for the same plain text, now you get completely different thing. Because now your ciphertext not only depends on the plain text, it depends on previous ciphertext. Not just the previous block, any previous, all the previous blocks. So this is called cipher block chaining, CBC. This is same thing in a different diagram, okay? And don't worry, they won't ask you to write these formulas, but this is good enough for you. And now for the decryption is the reverse process. So then why do we have initial value? I told you that I will explain what is initial value. Actually, you can guess why. If you look at the diagram, you can guess. Now you can see that other than the first block, all the other blocks you have two inputs here. So therefore, your algorithm assume that these two are first XORed and then take it as the input. But in the first block, you don't have such thing because that is your first block. So therefore, to make it consistent so that every block you can use the same algorithm rather than you have special variation for the first block, here also we give a dummy input, because in all the other states you get an input of the previous ciphertext. So therefore, here also we give a dummy input. That means we can determine what is your dummy input is. it's sort of a constant. So then it's consistent. Everywhere you have the same algorithm. So that is why we introduce IV. Okay, right. So you will find this IV in a lot of block modes. Okay, so that is the purpose of initial value. Now it's changed, so therefore a small change in one of the previous plain text can effectively change all the subsequent ciphertext values, which is good. Okay, which is good, which make it more stronger. Okay, right. So CBC can be used for hashing also. Remember hashing we did last class? So in hashing, what you need is not encryption. You need some hash value which represents your entire plain text. So this is a very good thing. Rather than you take this individual encrypted value, now you can see we don't take the encrypted value, right? Rather than you take the encrypted value, it's the same process, but we don't take the encrypted value. Rather, we just keep feeding it, and the final value is a representation of your entire message that you can write it as your MAC value, because that value depends on all your plain text or all your text. Okay, so that is called MAC base CBC or CBC for generating MAC. Why it is MAC rather than hash? Because we use a key. We discussed that the difference between MAC and hash. So this is hash. This is not a hash. This is a MAC because we use key, and this is my MAC value, which you can use to check integrity. Okay, right. So now we have discussed two, ECB and CBC, and also how to use CBC to generate MAC. The third one is CFB, cipher feedback mode. Right. So again, you don't need to exactly remember, because you can, after some time you will find that almost everything is the same, but actually every mode has little bit of a different thing. Little bit of a different thing, but you don't need to memorize these things. Now you can see the plain text is only given here. The initial value is given here, right? Which is slightly different approach. But anyway, so now don't memorize these rest of the mechanisms, but just remember the features. Cipher feedback mode, right? Cipher feedback mode. Uh, so here again, uh, so the small change in your plain text change your rest of the ciphertext, because you can see it's again chain. It's again chain, right? It's again chain. So therefore, you can see this ciphertext is the input to the next encryption. Next encryption. So therefore, the advantage of the previous uh, mode is still here. But at the same time, there's another advantage when you go for CFB. That is, it make your block cipher into a self-synchronizing stream cipher. This is a very famous question. Just make sure you remember this. So I forget to highlight it actually, because exam that is for examiner's favorite question. Okay, that is examiner's favorite question. So it effectively make your block cipher something like a stream cipher. Right? Something like a stream cipher, not a actual stream cipher. It's like it behaves something like a stream cipher. If you go for CFB, okay, if you go for CFB. So the next one is output feedback, OFB. OFB. OFB is another it's again we use the chaining, right? Again we use the chain. You can see that chaining is there, but in a different way. Right? This ciphertext is the input to next one. This ciphertext is input to the next one. So therefore, that errors are again getting propagated. But at the same time, small change in your previous plain text will change your entire ciphertext. That advantage is still there. Okay. And again, you need initialization vector. Okay. Uh, so that is called OFB. It's another approach. And the final approach is counter. So this is examiner's favorite mode, counter. And that one also turns your cipher into stream cipher. Not actually stream cipher. When you go for the counter mode, again, it's effectively acting like a stream cipher, but actually it's a block ciphers. So if it act like a stream cipher, that means it's faster. It's faster. Okay. So therefore, it's very good for high speed net encryption. So this is a very important property. Okay. So if you're looking for a very high speed stream cipher like behavior, you can go for counter approach or counter block mode. Counter block mode. Okay. Right. Again, you don't need to memorize the exact mechanism, but it's given in your UCSC note. But examiners have not asked you to draw these things. But just remember some features. In counter mode, we use something called known as. Okay. Which is a sort of a constant value. That is another additional input we use, uh, known as plus counter. But counter get changed. Counter get changed, but this is like a constant plus a counter. But counter get incremented in each encryption block. Right? That is why the word counter. Right? So the idea is, though your key is same, now every time you have another sort of a unique input given. Why it is unique? Because you change the counter. So therefore, even though the same plain text you take, your ciphertext change. But at the same time, here you don't have chaining. Chaining. No chaining, but now remember the one of the issue with electronic codebook mode was for the same plain text, you get the same ciphertext. But now for the same plain text, you get different ciphertext because your counter is different. And counter is also input. So therefore, count approach has all the advantages of uh, the simplicity and all the advantages of electronic code book. But at the same time, it hide patterns because of this counter. Right? It's very simple approach, no chaining, but at the same time, it hide patterns because of your counter. So this is therefore very popular because we want to make our life simple at the same time resolve any practical issues. That practical issue is now resolved because of every block is encrypted with the help of another input which is keep changing for each block. Okay. Right. So that is why this is examiner's favorite because this is one of the best, highly efficient and highly simple. At the same time, it hide all the patterns that were not effectively hidden in electronic codebook mode. Okay. And also you can do parallel encryption, decryption because there's no feedback, feeding the previous one to this one. So therefore now we can do it parallelly also. It fast. Parallel we can do high speed. Okay. You can see it has the advantages of ECB and those disadvantages are also vanish. So therefore this is better than ECB. Okay. Right. So this is a variation of count approach called GLOR GCM. GCM. So GCM is another variation of the counter approach. it also act like a stream cipher, and also it help you do the parallel computation because it's sort of independent. Anyway, this is just variation of counter. So you can, if you see GCM, you can consider it as a variation of counter. So all the features, advantages of counter is there. Okay. Then again, the diagram is given, but don't worry. I don't think that they will ask about this. Okay, diagram. Okay. So why they have mentioned about GCM? Because AES algorithm use GCM, which is a variation of counter uh, block mode. Okay, counter block mode. Right. So that's it about the block modes. Now we have discussed data encryption standard, DES, triple DES, AES, and also we discussed the padding schema, and also I think we discussed about 6 block modes. The best one is the counter approach. Counter is variation called GCM, right? Because GCM is used in AES. Right. I told you there are a few more block ciphers. So let's briefly look at those block ciphers. First one is IDEA, International Data Encryption Algorithm. Right. You just remember its key size is 128 bit, and it is used in pretty good privacy. You will learn about what is pretty good privacy in the very last topic. Okay. So there is another block cipher, symmetric key block cipher. So blowfish is another symmetric key block cipher, which is easy to implement, high speed, and it needs only very little memory. Those are the process of blowfish. So RC5 is another one, right? RC5. Remember, we mentioned all these things here, right? RC5. Then RC6 and CAS 123, 128. Only RC4 is stream cipher, right? Now we are into the RC5. So again, it's fast and simple. These are all block ciphers, right? Variable number of rounds, variable length keys, low memory required, high security. Right? Another block cipher, symmetric key block cipher. So cast 128 is another symmetric key block cipher. Key size again vary from 40 to 128 bits. Okay. Again, the number of rounds depends on your exact version. Right. So that's it about block ciphers, symmetric key block ciphers. Now we briefly look at symmetric key stream ciphers. So usually stream ciphers are weak uh, and they are very hard to use. Okay, so we will look at only one such thing, that is RC4. Remember, RC5, 6 are block ciphers, right? So so the stream ciphers are very weak ciphers because we use character by character, bit by bit, combined with XOR. So therefore, never use your stream key or the key because these are very weak algorithms. So you must take all the precautions, never reuse your key. Okay. Right. So the example is RC4 stream cipher. Right. RC4 stream cipher. It's a byte-oriented stream cipher widely used in SSL or web security. So that is the only stream cipher in your syllabus, mentioned in your syllabus. Okay. Uh, and you must never reuse the keys. So that is very famous question in exams. If you use RC4, which is a stream cipher, never reuse the key and use a very strong key, right? Very strong key. Right. So what are the symmetric key applications? So remember in symmetric key, same key is used for encryption and decryption. So therefore, we can't use this for general public or when you are communicating with so many others. So we can use it when you can trust the other part, like your head office and branch, or you have the 100% control about the both send and receiver. So this is not good for encryption, decryption in a web application and so on. There you need asymmetric key. But if you have the full control and if you have only few connections, like just one or two or few, like few branches, yes, you can use symmetric key in cryptography. But otherwise, this is not good for general applications. Okay. Or you can use this together with asymmetric key cryptography. That is another option. So you use asymmetric key cryptography with symmetric key cryptography, not symmetric cryptography alone, because symmetric cryptography alone is not practical when it comes to more users, because the big issue is how to send your key and also how to keep that secret, because you can't give it to third party because you decrypt using the same key, but you can give it to your branch system administrator, because that guy you can trust if you have few branches or your control, but don't use this for other general applications. Okay. Right. So the advantages are symmetric key algorithms are fast and simple. Okay. Uh, but the disadvantages are obviously you need to keep your key secret, which you can do only if you can have trusted party in the other side. And how to distribute your key to that guy is that part is another one, because that key you use to decrypt, then it's like a chick and egg story, right? How do you send your key secretly? Then if maybe you can say then we will send it as a symmetric key cryptography. So then how do you send that key? Right. So those are the practical problems. So therefore use this only when you have a trusted party and you have a trusted way of giving your key to the other side. Okay. Or maybe you can go and physically configure it in that site. So therefore key distribution is real challenge when it comes to symmetric key cryptography. That is one of the issue prevent using symmetric key cryptography for general usages. Right? So there are some solutions, not perfect solutions, bit of solutions are there that again we use when we have trusted party in the other side. Okay, right. For example, now if you want to communicate with three parties, and if you can't 100% guarantee their trust, you need three different keys. One key for this communication, another key for this communication, another key for this communication. But then if you have 1,000, so then you need 1,000 keys, because otherwise this, if you use the same key here, which you use to decrypt also, then if this guy got access to this data, he can decrypt because he has the key. Because the same key that we use to encrypt is used to decrypt. So therefore, they can cross hack. Okay. So therefore, if you have 100 senders, you need to give them 100 keys. Then each data you need to decrypt using then you also you need to use 100 keys and relevant key for the relevant data. That is if you are communicating with multiple parties. What about if you have three parties and they want to communicate with each other? Three keys. Four parties, one, two, three, four, five, six keys. Likewise, keep going, right? Say four parties. This is the formula. This formula you need to remember. The number of keys if you have four parties communicating with each other. N is 4. 4 into 4 minus 1, which is 3, divided by 2, 6 keys. Yes, 1, 2, 3, 4, 5, 6. For each communication, you need key pair. So that means if you have 10, say 1, 2, 3, 4, 5, 5 into 4 divided by 2, you need 10 keys. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you need to remember this formula. Okay, so that is if they want to communicate with each other. Right? So 5 parties, but 10 keys. Then 6 parties, 6 into 5 divided by 2, 15 keys and so on. You can see it grows like exponential. That is why this is not very practical because we can't use the same key because then each one can hack others' data because the same key is used for decryption. Okay. And another solution is, of course, this is not a solution, this is a problem. When it comes to distribution of the key, we can use a key escrow. Right? It's a key distribution mechanism. But again, that is not a perfect solution. Rather than you distribute from your side, you ask your senders to get it from the key escrow, which is a trusted third party to keep your key. But anyway, that is not a perfect solution. That is maybe at least reduce that burden from you to a third party, trusted third party. Okay. It's something like keeping your important documents with a lawyer and lawyer handle it for you. Okay. So then they get the key from the escrow agent or key escrow rather than from you. So then you don't need to do the key distribution. So escrow agents is its task is securely distribute your key to the senders. Okay. So therefore, if someone talk about key escrows, it is not encryption algorithm or cipher blockchaining block mode. It's or padding schema. It's a key distribution protocol for private keys. Protocol or mechanism. Okay. But again, key escrow is also relative concept because how can we trust and key escrow are they technically solid? Those are challenges. Okay. Right. So the final subtopic is perfect forward security. So this is also related to symmetric key cryptography. So remember, we use the same key for encryption and decryption. The key that we use to encryption is used for decryption. Okay. So therefore, if someone lost the or someone hacked the encryption key, same key is used for decryption. Now, if someone that guy has got some past ciphertext, he can he or she can decrypt all the past ciphertext also because you have been using this key for last 10 days, last 1 year. Now, if this guy has collected all the previous last 5 years of ciphertext, the moment this guy got the key, now this guy can read all the old messages. So far, he was not able to read those messages. That is a risk. But if you want to eliminate that risk, or if you prevent that risk, we call it perfect forward security. So it is a security feature in cryptographic system that ensure that even if a secret key is compromised means revealed. In the future, the past communications remain secure. So if your key is revealed today, the yesterday and day before ciphertext must still be secure. Maybe today's one is revealed, but not the past things. How to do that? It's very simple. It's very simple. So what is the solution? So use new key pair every time. So then if this key is revealed, only this data is compromised. All the previous data is not compromised because every previous data we use different key. So that is, if you do like that, then of course there's a challenge of key distribution again. If you have a solution for that, then you call it perfect forward security. Right? Perfect forward security. Because you don't reuse the same key twice. Okay? So then someone will say, how do you make sure that you don't reuse the same key twice? Because how do you send the key? So you don't need to always send the key secure manner to the other side manually. There are algorithms to agree keys secretly. So if you can do that for every transmission, we can agree a new key. So then you get the perfect forward secrecy because every transmission you agree a different key. So then you need some mechanism to agree a key in an unsecure network because still we have not done the encryption. So there are mechanisms to do that so that you can go for a perfect forward secrecy using private key cryptography. So which includes Diffie-Hellman and its variations. So we will look at these in a separate topic. Key distribution challenges are handled in a separate topic in your syllabus. But just remember, if you go for these techniques rather than you manually distribute your keys, you can agree unique key for each and every transmission. So then you get the perfect forward sequence because if your key is revealed for this session, only this data is compromised. All the previous data, though that hacker has collected all your ciphertext, those are not compromised because for each session we use separate key. Each session we agree the key using these algorithms. And we will look at those things in a later topic. Okay. Right, past papers. Right. So these past papers are now very straightforward because examiners ask only sort of routine questions, but you must have idea so that you finish your studies well before the exams. Okay. And also you can spend less time because you know what are the things you must remember, what are the things you don't need to pay a lot of attention. That is smart study. Right. This is 2024 question 1B. Right. This is from your last slide. Perfect forward secrecy ensure the future communications remain secure even if the private key is compromised. That is exactly right. So if today's private key is a compromise, the future things are not going to be compromised because tomorrow we are going to use a new key, right? Or tomorrow means for the next set of data transmission, we are going to use a new key. So therefore that just because this key is compromised or revealed, you are not going to get the next set of data decrypted. Okay. Okay. Right. So therefore, why this is false? Because this says future. It's not future. Anyway, this is also in a way correct. Right. Today's one is compromised means future ones are not also compromised, right? Because future we are going to use different thing. But the proper definition is, right, when we say perfect forward secrecy, when today's or when this session's key is revealed, your past data is not revealed. That is the proper definition. But actually, this is also correct, but this is not the way we define it. Right? For when this session's key is revealed, all the past ciphertexts are not in trouble because these cases we use different keys because every time we use different key. But anyway, technically this is also correct, but this is not the proper definition. Proper definition is when this is revealed, these are not still revealed. Okay. Past communication remains secure. So therefore, examiner has taken it as false. Actually, I thought this is also correct, but examiner has taken it as false because examiner has gone for the proper definition or exact definition of the perfect forward security. Okay. Right. So then just key sizes, block sizes, they ask. The advanced encryption standard AES algorithm encrypts 33 bytes of a plain text message to a 33 bytes of ciphertext message when it use count operation. So remember, counter is the last block mode. It has all the advantages of electronic code book. At the same times, it hide the patterns because of the use of counter. So every counter value is unique, right? So if your plain text is 33 bytes, your ciphertext is also 33 bytes because it's a very simple approach. Anyway, almost all the algorithms, the size is the same. Okay, size is the same because you just XOR with your counter, your plain text block XOR with counter, right? Remember? You can see this is your plain text. Sorry, this is your counter and not non-ands. This is your plain text. You XOR with your counter value. So when you XOR, if this is 1 byte, this is also 1 byte. Just XOR. Okay. So therefore, if you have 100 byte, your result plain ciphertext is also 100 byte. Okay. The answer is true. Right, next one. Why symmetric key encryption is still widely used despite the availability of public key cryptography? So remember, public key cryptography is better because then you decrypt using different key than the encryption key so that you can keep your secret with you. So then the question is still, when you have that approach, why do we still use symmetric key? We simply use symmetric key because it's efficient, simple, and it's good enough when we have trusted senders. Okay. And because this is very simple, right? Because the decryption is the reverse of the encryption. Performance because it's simple, simplicity, right? But yes, limited usages. Right. 2023 question 1. C. AES algorithm encrypts 30 bytes of plain text message to 32 bytes of ciphertext message when it uses counter mode. Remember, when it uses counter mode, your ciphertext is of the same size as plain text. I think this is 2024 also the same question was there. Right? So if it is 30 byte, if you use counter mode, the ciphertext is also 30 byte. So you need to say false and explain. Okay. False and explain. Explain how the counter mode work. It just XOR the plain text block with your counter or counter plus nonce. So therefore, if your block is 1 byte, ciphertext, plain text is 1 byte, ciphertext is also 1 byte for that block. This happens for each block. So therefore, for 30 byte plain text, you get 30 byte ciphertext. Right. Next one. What is the primary disadvantage of a symmetric key cryptography? So you need to select and explain. Though this looks like MCQ, you need to select and explain. Right. What is the primary disadvantage of a symmetric key cryptography? Slow? No, right? Symmetric key cryptography is faster. That is the right. Requires secure channel for key exchange. Yes, that is the issue, right? So you need secure channel to key exchange or some algorithms like Diffie-Hellman because you are sharing your secret, your decryption key with the sender. Yes, that is a disadvantage. Key distribution problem. That is also disadvantage. Okay, that is also disadvantage. Now you have two answers. Vulnerabilities to brute force attacks. So that also can happen, right? Any system is vulnerable to brute force attack. Any system. That especially these symmetric key cryptographic systems. So anyway, this is also correct, but they ask primary disadvantage. So therefore, in these questions, usually only one answer is correct, right? though they don't tell like that, but it says prime because if you go to the go through the past papers, for the last three past papers, you get this kind of MCQ like questions. I have seen that everywhere only one answer is correct. And here it says primary disadvantage. Right. So it should be two or three. The key distribution problem is the general answer. So I will go for the general answer, but because secure channel for key exchange is also there, but there are some without secure channels, there's a way of key exchange also. There's a way of key exchange also. Like diffelman, you don't need secure channel. So therefore, this is not always correct, which you will learn later. Okay, diffelman, key agreement, and so on. But this is generally correct answer. So therefore, I go for the general answer. Okay, I'll go for the general answer. Yes, so general answer they have taken. Okay. General answer they have taken because this is not always correct, right? Right. The second one, because there are alternative techniques for that also. Right. Next question. Which is the key length of the advanced encryption standard? So that of course from your note, right? So that you need to remember and right. So there are actually three sizes: 128, 192, 256. So out of these, 192 is in your answers. So therefore, answer is second one. Okay. Right. So then 2022. Suppose we have nodes A, B, C, D, E, and F in a network. We have to generate total of 10 keys to let every node communicate with every other node in bidirectional secure way using AES encryption algorithm. First of all, you must know that AES is symmetric key. Right? So they don't say exactly symmetric key because remember in the exams, you don't know whether this question is from which topic, right? But the examiner has mentioned AES, that means symmetric key. So if you have A, B, C, D, E, and F, and they want to communicate with each other like this, and so many ways, right? I just draw few of those, right? So then remember n into n minus 1 divided by 2 if everyone is communicating with each other. So how n is 1, 2, 3, 4, 5, 6. 6 into 5 divided by 2. You need 15 keys if everyone is communicating with each other using symmetric key cryptography. So the answer is 15, but this says 10. So you need to say false and you need to do this calculation and say that it is not 10, it is 15. Okay, it is 15. Right. So the next one, data encryption standard algorithms encrypt 30 byte of plain text message. So you have 30 byte of plain text to 32 bytes of ciphertext message when it uses electronic codebook mode, ECB, right? And the public key cryptographic standard, PKCS5. So that is the padding standard. That is the padding standard. So the padding standard is this, and it has 32 byte of ciphertext. Sorry, it has 30 bytes of plain text. And this says you get 32 byte of ciphertext. Right? So 32 byte of ciphertext. So what is the block size? I can't remember the block size of DES. You need to remember that, okay? DES block size. Block size is 64 bit. That means 8 byte. 8 byte. That means 8 byte. Block size is 8 byte. Now you have 30 byte, okay? 30. So therefore you break it into 8 bytes. 8, 8, 8, 8, 16, 24. This is your last one because every block must be 8 byte. But you have only 30 byte, but remember it will be ultimately 32 byte because your block size is 8. So 8, 8, 8, 24. Now you have 6. But 6 is not your block size. So therefore you need to PKCS will add 2 bytes to make it 8 byte. Right? So therefore now it's something like your plain text is 32 byte, though it's actually 30 byte because of the padding. And each byte, 8 byte will be a ciphertext also 8 byte because this electronic code book. So remember ECB and counter, your ciphertext is same as plain text, but plain text after padding. After padding, because each block is of the same size. So therefore after padding, right? Just because 30 byte, don't say 30 byte. After padding, this is 32. So therefore your plain ciphertext will be 32. So therefore answer is correct. Answer is true. You need to explain this, right? You need to explain that 2 bytes are padded. So then each 8 byte is 8 byte ciphertext. So therefore your ciphertext will also be will be 32 byte, not 30 byte. Okay. Right. Last block will be padded with 2 bytes. You can mention that padded with 2 bytes also. Or maybe you can draw a small diagram. Right. 2022 question 1I. This is a 2022 paper. Counter mode encrypts plain text faster than cipher block chaining mode. That is obviously yes, right? Because counter block is we can do parallel. There's no chaining. Right? There's no chaining. Remember, counter block has all the advantages of uh, electronic code book plus patterns are hidden because of the counter. So the answer is true. Okay, because CBC is chaining. Chaining take time. Okay, we can do parallel processing in counter mode. But CBC you can't do parallel processing because second block depends on the first block ciphertext. Okay, right. Next one. Which of the following is not type of symmetric key? That is super easy, right? Symmetric key cryptographic system. Remember, we already discussed about data encryption standard, right? DES, triple DES, AES. I told you Diffelman is a key distribution protocol. It's not a symmetric key cryptographic protocol, right? So therefore, this is not a symmetric key cryptographic protocol. This is key distribution protocol. So therefore, this is possible answer. Now, Caesar cipher is there. Actually, Caesar cipher, you don't need a key. So therefore, this is pretty much little bit debatable answer. But Caesar cipher is in a way symmetric because same algorithms reverse is used for decryption, right? Here you add 2, so add 3 or 4, whatever. So then you subtract. So if A become D, your D become A. It's symmetric. But actually, I don't know whether it's use a key, right? But anyway, it's symmetric, right? So therefore, we have anyway it's symmetric, and usually you have only one answer. But this is definitely not an algorithm. This is key distribution protocol. So therefore, we need to take that. But this is little bit debatable because this doesn't have a key actually, but it's symmetric, right? It's symmetric. So anyway, I think the examiner will go for Diffelman because Diffelman is not a encryption decryption algorithm. Anyway, Diffelman we will do later, right? In a session. Right. Third one examiner has taken because it's key distribution protocol rather than encryption decryption algorithm. But C cipher is little bit debatable because typically C cipher is symmetric but not using a key. Right. Which of the following is not a mode of operation for block cipher cryptography? That is super easy. These are all the modes we discussed, some of the modes, but this is a padding mechanism. This is a padding mechanism. Okay. You can see this, if you prepare this properly, this subject is super easy, but you need to plan, manage, organize, and study, right? Not study when exam is 1 week away, right? Fourth one. Right. Again, they ask about the key sizes, of course, that you need to remember. Okay. That is your task. Right. Next one. Which of the following is the main disadvantage of electronic code book? Remember the ECB, the main disadvantage is if you have the same block, you get the same ciphertext because it's block by block. And that disadvantage is eliminated by count approach. So therefore, what is the main disadvantage? It is prone to cryptanalysis since there is a direct relationship between plain text and ciphertext. For a given plain text, you always get the same ciphertext because no chaining, no unique value for unique input, right? So some approaches do the chaining, a count approach rather than doing chaining, it give a unique another third second input. The answer must be third one. Okay, that's it. Okay, so that's it about uh, symmetric key cryptography. Actually, we finish it because otherwise we waste time in the next class also, right? Now, in the next class, when we do security, we can freshly concentrate on asymmetric key cryptography. That is our uh, next topic in security. Okay.